things like that.
Yeah. And then they were just talking to these two guys for a little bit, and they were trying to get this up, and they said, I think it's 10. I think it's 10 and 11.
However, it was just recently announced that it's going to be offered as a crate engine. It is a 755 horsepower, 715 foot-pounds of torque engine from the factory. We do hand build these engines in Bowling Green, Kentucky at the Corvette assembly plant. With me here today, I got Brad Doffenbaugh over here. He's our manufacturing engineer. Two of our engine builders, Richard LaRue and Jason Neal, and then myself, Nathan Grigsby. I'm the lead quality engineer for the Performance Build Center. So at the Performance Build Center, we build 100% of the LT5 engines for the Corvette. We are also going to be hand building the crate engine. We build 100% of the LT4 engines, and we build 100% of the LT1 manual engines for Corvette. So we got quite a bit going on in our shop. We build anywhere from 45 to 60 engines a day. Each builder builds between 2.5 and 3 engines per day. Got about 40 engine builders that work for us there. So we are still considered a very low volume plant, very low volume facility. We're definitely not the most efficient, but we specialize in the extremely high performance aspect of GM. One thing that our facility does offer is the customer build program. So if you buy a new Corvette and you want to pay a little extra, you can come in and build your own engine. The way we do that is we bring you in and set you up with an engine builder, and you can do every single fastener on the engine, somewhere in between. And you start with a bare block just like this and go up, take it all the way through a testing equipment, and we'll actually put gas in it and fire it up at the end of the day. So with that being said, we're going to go ahead and get started on the actual build process. So when you come into our shop, we have 18 stations that we build this engine at. Today we're not going to see that just for space reasons, obviously. But the first thing a builder would do is they would have this bare block that they would pick up off the dunnage at station 0. They're going to lift it up in the air with a hoist, do a bunch of inspections, looking for anything like rust, porosity, any kind of non-conformancies that they wouldn't like in an engine. After they do that, they're going to clean it real well with some alcohol and rags and then mount it to our engine cart. Next thing up is going to be our camshaft. So Jason's holding up our camshaft here. This is unique to the LT5 engine. It's still a small cam that's in most of the LT series engines. Something I do want to point out while we got it out like this, you're going to see a tri-lobe on the back of the camshaft. That tri-lobe is what actually actuates our fuel pump for the high pressure fuel system. The high pressure fuel system is run off of the camshaft itself. Throughout this process, I'm going to tell you a couple things that you're seeing that isn't like our process in day-to-day. First being, we're not using any type of assembly lube. In our normal day-to-day process, this engine would be dripping in oil as we're putting it together. That's what this real nice cart down here is for, is to catch all that excess oil that's running off the engine. Just for cleanliness reasons in our demonstration engine build, we don't use any kind of assembly lube. Richard just installed what's called a widget on the back of the camshaft. What that's doing is that's holding that camshaft in place and is actually timed to the camshaft to top dead center. So now that that's in there, that camshaft won't come out, and also it's set up for when we go to put our timing set on it. Jason's going to go ahead and install the camera.
It's looking to have a certain amount of good hits, so when you see them use that torque gun, sometimes you see a little green light, that's when it knows it got a good torque. We have a lot of controls on our torques. We're looking at angles, so if we see a rise in torque too quick, they could have cross-threaded the bolt and it won't allow them to continue torquing it. So they'll always get a good hit, and then to get the right number of good hits before allow them to keep going. And as they go station to station, it'll look at the prior one before it'll allow them to go on.
So what Richard's doing right now is he's installing what we call oil squirters. So Richard, you hold one of those up real high, everybody can see it. What that is the little squirter that goes into the oil gallery of the engine and squirts oil up into the bottom of the piston. One, to help keep it lubricated, and two, to keep it cool. So that's what we use to lubricate all that and keep the wrist pin well lubricated and cool. There is one for each cylinder on that, so there's a total of 8 in the engine. Something else we'll go ahead and talk about while we're here. If you look in, we've already got the upper main bearings installed in this engine. You'll see there's 2 different colors. The LT5 has a unique leaded bearing, main bearing in it. So that's what kind of gives that gray color in those 4 outer bearings. The middle bearing is kind of a red color. That's a Teflon-like coating. That's what we call our thrust bearing. You'll see there's a kind of a washer on either side of that. That's what holds the crank into position front to back and gives us our end gaps. Next up is our crankshaft. So again, another unique part to the LT5. We did have a new crankshaft made. You can see it's kind of got this nice gold color to it. That's from the different material properties, different heat treating process that we have on that. We had to do that, make it a little bit stronger, a little bit tougher to support that extra 105 horsepower over the LT4. Main caps are next. So these are a steel main cap. They are unique to which spot they go in. So if you look on top of them, they are laser etched with the direction that they have to face and where they go as far as a numbered position. They are numbered 1 through 5. The reason behind that is when these blocks are machined in Spring Hill, Tennessee, they run a precision bore down the center of it with all the main caps in. Then they go in and do a final honing. What that does is it makes it a unique main cap to that block and engine. Something else you're going to see us doing, you see us loose installing all our fasteners here, so we do this in our shop too. We use these battery operated pencil guns to loose install all our bolts and all our fasteners prior to torquing. The main caps are a press fit, so you can see Jason's going to tap those down. This engine's been torn down and put back together multiple times, so all the clearances on it are kind of messed up and not correct, so he's not having to tap too hard. But in our normal day-to-day process on a virgin engine, we have to hit that pretty hard to get those seated. So again, here's something else that's different out of our ordinary of our process. We normally have a multi-spindle that comes across and torques 2 bolts at a time on these. So we torque the 2 inner bolts on all the main caps first, and then we torque the 2 outer bolts on the main caps after that. Jason's going to use this torque wrench for today just because we can't bring that kind of big, expensive equipment with us. And he's going to follow a similar torque sequence. You kind of see him jumping around between different main caps. So that's the same torque sequence we use. However, with our multi-spindle, we torque 2 at a time rather than just 1. We do consider this engine a 6-bolt main. You can see Richard's installing side bolts in it now. So there's 1 on each side of the main cap. The main caps are what's considered an entrapped main cap. So if you see the casting of the block itself is higher than what the main cap is. While we're doing that, let's talk a little bit about this reluctor wheel on the back of the crank. So if you see, there's like what looks to be a gear on the back of the crankshaft. What that actually is a reluctor wheel with teeth on it that the crank sensor is picking up off of to know where the crank is positioned. So we can read those gaps between each teeth to kind of give us an estimate of RPMs, where the crankshaft's located. That's how we adjust all of our variable valve timing, any kind of direct injection, or any kind of fuel sequence stuff that we do. This LT5 engine, like the LT4 engine, does have a 10-to-1 compression ratio. The crank itself has a 3.622-inch stroke. So Jason's got our crank sensor here. So like I said, on that reluctor wheel, that crank sensor is what's picking up the teeth on that reluctor wheel so that we know where that crank is at. Richard's holding up our EOC fitting there. So that EOC fitting is going to go in the side of the block in the water channel, and that's actually what's going to get our antifreeze from the block into our oil cooler. A little later on you'll see us install that oil cooler and it'll make more sense, but just kind of a quick disconnect fitting so that we can run a hose to plumb our oil cooler into the engine. So kind of give you an estimate where we'd be at in our build process. We'd now be moving into Station 3, which Station 3 would be our piston install or stuff station. This is going to be one of our longest stations of the build. It takes us about 10 to 15 minutes to install these pistons. And a lot of it is because of the inspection process that the builder is doing on the piston itself. In the normal build process, they're looking for things like the orientation of the rings, if they're flipped upside down or not, making sure they're 180 degrees apart. They're looking for any kind of FM in the skirts, and even the C-clip on the wrist pin. So they give a very thorough inspection of each piston prior to installing it. The pistons themselves are a forged piston. They are unique to left and right side. So they do have a letter on them that says if they're left or right. And they also have an arrow to point towards the front of the engine. The reason behind that is because of the valve clearancing that's put into the piston itself. We have to have it in the right spot to make sure we don't have a valve contact on piston. The rods are powdered metal rod. So it's actually a metal powder that's put into a mold and then compressed to give us that powdered metal rod. It is a forged rod. Very, very strong. Something else, Richard, you want to hold one of those up? These rods are considered a fractured rod. So what I mean by that is we actually break these rods. So they're casted or forged in one piece. We then laser etch the inside bore. We slide it onto a mandrel and then expand that mandrel and it cracks the rod. What that does is it gives us more surface area for those to bolt together. Makes it a lot stronger connection, a lot stronger joint between the cap and the rod itself. What that also does is it makes the cap unique to the rod. You cannot switch caps and you cannot turn them around. They have to go on in the same orientation they were forged in. Some of the people that just showed up, I do want to reinforce who we are and what we're doing. So we are the Performance Build Center from Bowling Green, Kentucky at the Corvette assembly plant. We handcraft these engines. This is the new LT5 engine in the 2019 ZR1 Corvette. It's also just recently announced that it's going to be offered as a crate engine. If you're interested in the crate engine, want to know on pricing, availability, any of that kind of stuff, please go over and see any of the guys in the red shirts. They're going to be one of the dealers that's selling these engines for us. And again, please feel free to ask any questions. This is very informal and open to conversation. So now that we're finishing up our piston install, we're going to move to the next station in our build process, which would be Station 4. I'm going to go ahead and pass this station over to Brad, let him talk about the special test equipment and tools we got at that station.
Yeah, so what they're going to do is they're going to pull this cart into a station and lock it down on the floor. There's a little piece of strip over there that's going to pick up on a laser photo eye, so we know the cart's in the correct spot. what they're going to do is they're going to bring the machine over. They're going to touch on 3 points of the engine, the end of the main bearing caps, and then the first rod bolt. What that's going to do is it's going to teach those encoders on that smart arm where that spindle is in space. It's going to track them as they move that machine through each rod cap to make sure that they're on the correct rod cap and won't let them torque one, miss one, or torque one out of sequence. This is a good example of one of our torque plus angle joints. So we're not actually targeting a certain torque. So we're not going to say torque the rod bolts to 65 Newton meters. So what we actually do is we torque it to 20 Newton meters and turn it exactly 85 degrees, and then whatever that resulting torque is, we accept that as long as it's within a certain range. So depending on the friction between the threads and under cap of the bolt head to the rod, your torque will be a little bit different, but the clamp load and how much that bolt actually stretched will be the same. So all of our critical fasteners, we use that torque strategy with. So your main bearing caps, your rod caps, the head bolts, the balancer bolt are all a torque plus angle controlled joint. So the next thing they'll do, they'll level out the block just like this, and then they're going to hook up torque to turn. So what torque to turn does, it's a machine that's going to clamp onto the engine block, and it's got a little electric drive motor and a torque transducer that's going to hook up to the front of that crank. We're going to spin the engine over and measure how much torque it takes to turn that bottom end assembly. So as Nate mentioned earlier, if you were to mix up one of those rod caps, the engine, those bores won't be perfectly circular anymore. So as it tries to turn, it'll be slightly tighter. So, you know, down to the 1/10 of a Newton meter of change in torque, we can sense if there's a defect in the engine. So we'll check that torque, make sure it spins over easy. While the engine's turning over, we're going to measure the width, height, and distance between every one of the reluctor ring teeth on the reluctor wheel back there. It is a 58X reluctor ring on the LT5. And then it also will have 2 accelerometers, one on each side of the pan rail, that's looking for vibrations. So if we were to have a missing rod bearing, if they would have forgot a thrust bearing or anything that has some crankshaft in play, anything putting vibrations or knocking through this engine block, we will pick up on that. And then one final thing I'll talk about, and it's hard to see right here, but we have barcodes on all these parts. So on the block cam crank, they're going to scan those. They're going to scan their engine. It's going to say, hey, I have an LT5, I'm trying to build that. As they scan those parts, it has logic built into it, say, hey, that's not an LT5 crank, I'm not going to let you do this. So that's part of our air-proofing techniques that we use, that we scan all these parts as they are assembled, make sure that the right parts, and we track those on the engine. So this engine, if it was ever in a car and something happened, we can know exactly what serial number, crankshaft, and Nate can look up to find any details on that we would ever need. So once they get a green light from that, they'll allow the engine to keep going through the process because we have validated the bottom end of the engine.
So now that we got our forged bottom end together, we're going to go ahead and put our actuator and timing set onto the engine. So Jason is installing our chain tensioner right now. Then he's going to pick up our crank sprocket, timing chain, and our actuator. So when I say that actuator, that's what gives us our variable valve timing. So Richard's holding what we call our cam bolt. However, what it is a valve. So you can see there's a little plunger on the top of it. And what that plunger does is it can direct oil flow. You see the orifices in the side of the valve. When that goes in through that actuator, when there's a solenoid on the front cover that actuates and pushes on that plunger and changes oil flow into our actuator, which can either advance or retard timing. Brad, you want to give a little bit more spec on the timing itself?
Yeah, so you can see here, this is the trigger wheel. There's 2 small tabs and 2 big tabs. That's how the cam position sensor knows where it's at as those are spinning. There's 2 springs that you kind of see back here that holds it in its park position. So the park position is 7 degrees advanced cam timing. And then in cold test later, we will take that through its full range of authority, which is 62 degrees. So this cam phaser can go from 7 degrees advanced cam timing to 55 degrees of retarded cam timing.
Next thing's up is our oil pump. So this is a variable displacement oil pump. What that does for us is we're able to change the amount of displacement or pressure or flow of oil depending on what kind of elements the engine's in. So if we're cruising down the road at 2,000 RPM with very little load on the engine, we can back that oil pressure off or oil flow off. 1, to help with fuel economy, and 2, to help protect the engine. When you don't need real heavy displacement or high pressure, it's not good to run that on an engine. You want to back that down. On the opposite side, if we're drag racing the engine and it's under very high load, we can bump the flow and pressure up to make sure we're protecting the engine on that side. Just a supplier note on this oil pump, it is a melling oil pump. Next thing up, after we get our cam bolt tight, we'll do the next thing. Now we're going to go to our front and rear cover install. So today you're going to see that there's no gasket or any material on these front and rear covers, and also the oil pan. However, when we normally build this engine, we put each of those into what we call RTV. The RTV machine goes in, we put the piece into it, and then it's a CNC robot that comes in and puts the exact amount of RTV as a bead around the pan. So it is CNC'd, so all of them to get the same amount and in the same placement. Brad, you want to talk a little bit more about what RTV is looking for and how it works?
Yeah, so on the RTV machine, what it's doing is it has a camera system that's going to validate that the bead was correct. So as you can see on that oil pan, there's a ridge where that RTV bead would need to be applied. So it takes a picture and picks up on that ridge. After the RTV is then applied, it takes another photo and can determine the entire width of that RTV bead and make sure it's within spec, and also check for continuity. So just in case there had been an air pocket or a bubble that would have came through that system and left a little spot of no RTV, we can catch that in the system. And then also, because these engine builders, they put their name on it, they build their entire engine themselves. We also have a lot of visual inspection. So even though we have a camera system and air proofing to validate that the bead is good, the engine builder will look at it and make sure they like it as well before they install it on the engine.
So I just had a question over here. I know probably a lot of people weren't here for when we talked about this the first time. The question was, what about this torque gun up here and what are we scanning? So what we're actually doing here is when a builder scans that and you're hearing that beep, it's opening up what's called a P-set. What that P-set does is it tells that box what torque it needs to be. So if a fastener's got a different torque, when it scans it, let's say it's 10 Newton meters, it's going to tell it, hey, you need to torque 5 bolts at 10 Newton meters. It's also going to be checking for things like how many degrees the bolt's turning. That way we can't torque the same fastener twice. It won't let you do that. So it's checking to make sure you have all those torques. Let's say it says you need to torque 5 fasteners. If it doesn't see 5 good torques, it won't let you go on to the next step. So that's a lot of air proofing for us that does a lot for our quality.
So yeah, you can see it on there right now. On the next torque, I'll have Jason pause for just a quick second. And I'll kind of explain what Nate was talking about there. So here in a second, you'll see it flash 10.44. So that torque at 10.44 Newton meters. And then the second number that'll flash, if you see it, it will be the angle that it took to get there. So as long as it starts to see a threshold, usually around 1 to 2 Newton meters, it's measuring how much angle it took to get to 10 Newton meters. If you had a really spike increase in torque, it's likely cross-set or there was something wrong with that joint. So we use that as a lot of protection to make sure that we don't improperly install or cross-set a fastener.
Yeah, so we had a couple questions, about how we do this at the plant, how long it takes our builders to do things. So these builders build between 2.5 and 3 engines a day, depending on if we're on an 8-hour or 10-hour schedule. They build them in about 2 hours each. We do use these torque guns on all of our joints, and we do track every torque that we have for the life of the engine. Like I said earlier, our stations are set up, or our line is set up to where we have 8 individual stations. So each station will have a torque box, at least one torque box that we use at that station. When they go to the next station, they're looking for what is called a flat line up on the box. All the boxes talk together, so if they don't complete all the torques in one station, when they go to the next, it won't let them do anything. It makes them go back to the previous station to finish the job before they can continue. So we'd have our oil pan on now. Like I said before, the oil pan would also go through that same RTV machine. This is also a dry sump oil pan. The LT5 is 100% dry sump engines. Both in the ZR1 and the crate engine will be offered in a dry sump only. Just some kind of cool facts about this. At any given time, the engine has about 3 quarts of oil in it. The total oiling system is 12 quarts on a dry sump. So what that does, it helps us keep the oil cool because we have so much more. Also keeps it cleaner longer. And the big reason is for track and performance reasons. We don't have to worry about that oil sloshing from side to side or being dry spots when we're going around corners.
How much vacuum does that pull, do you know?
So the question was, how much vacuum does it pull? I couldn't answer that right offhand, I'm sorry.
I know in cold tests, we measure it in kPa, but to break it down in PSI of oil pressure, on the high pressure setting, it's around 70 PSI of oil pressure. On that lower oil pressure fuel economy type setting, it's around 40 PSI.
So if you're here earlier, we talked a little bit about this EOC fitting we installed in the block on the water channel. What Jason has here is our oil cooler. So there's actually a black gasket where we connect to the oil pan where the oil flows through the cooler. But that EOC fitting up on the top is what's going to allow the antifreeze to come from the block into the cooler itself. The EOC fitting in the front of that's what's going to deliver the antifreeze back to the radiator.
So one thing you'll notice here on the LT5 that's specific to it is these ports on the top of the block have rivets put in them. They would usually do that at station 0, but we don't have a rivet gun here, and you can't really get them back out, so we leave them in it. But what those typically would be for is for the AFM cylinders, or active fuel management, where the engine goes into V4 mode. The LT5 does not have that, so the LT5 always runs on 8 cylinders. What those typically would go to is in the valley cover, or on an LT4 and LT1, we call it a LOMA, for lifter oil manifold assembly. Those oil would go to those solenoids, which would then go to the AFM lifters to collapse the pan, allow those lifters to ride on themselves and deactivate cylinders 1, 4, 6, and 7. But because of that, we have a normal valley cover that doesn't have those solenoids. We go ahead and rivet those holes shut so we don't get any oil pressure fluctuations from oil that might have seeped out through those.
Next thing we got here, Richard's holding, is our mega lifter. So if you're here earlier and I got to talk a little bit about the camshaft and the tri-lobe on the back of the camshaft, that mega lifter rides on that tri-lobe, and that's what's going to power our high pressure fuel pump. So our high pressure fuel pump is driven off of the cam. That's just a traditional roller lifter, a little bit larger barrel. There's no hydraulics in it or anything, so there's no oil delivery to that. So our next thing is going to be our lifters. Like Brad said, this is a non-AFM engine, so we do have traditional hydraulic roller lifters or hydraulic valve lash adjusters. These do adjust lash hydraulically, so there is no valve adjustments ever needed in these engines. So to see how to have it, some of the things they're doing, inspecting the pieces, they're checking for things like no FM in the ports. They're making sure the rollers roll freely and smoothly. Today we're just kind of putting the engine together, but in a normal process, each builder's inspecting all of these parts very thoroughly. Next up is going to be our head gasket. So this is a 7-piece or 7-layer steel head gasket. You'll see there's 2 dowel pins in the deck already there. We do put those in at this station, but however we got them left in for the engine for today. On top of that head gasket, we're going to put our head. So the head, Jason, hold that up real quick. One thing I do want to point out, on the bottom side, there's a different bolt. There's a black bolt in that. Brad, you want to go ahead and tell them what that bolt does and what it's there for?
Yeah, so that one bolt has to be shorter in a different material because there's a coolant cavity that if they drilled it and tapped it at the same depth, would go right to that coolant cavity. So that one bolt is an Allen head instead of a normal cap screw bolt. And we have a machine we call Big Bertha, which is a 10 spindle, multi-unit spindle that's going to torque down the entire head, all 10 bolts at the same time. So it'll run them down snug, reverse them, and then do a torque plus angle controlled fastening on it. One thing that's cool that we have, part of our airproofing, when we know that is, we have a tray of sockets that has a proc switch with, it knows which socket is in which one. So when they do their first head install, it has to see that the Allen head screw socket is removed and the normal socket is installed in the other tray to allow it to do that torque. Because that bolt is shorter, it's a higher tensile unit steel, so it's got a slightly higher torque than the other one, so we have to ensure that we torque that one bolt to its proper torque spec.
So I do want to talk just a little bit about the heads themselves and some of the specs on them. So they are a 65.47 cc combustion chamber. Some of the valves are really cool in them. So the intake valve is a titanium valve. If you know anything about the wear properties of titanium, it's very poor. So we put a steel wear cap on top of all the titanium intake valves. You can see the little cap that's over that valve stem in there. On the exhaust valve, we do run a steel exhaust valve, but it's liquid. It has a liquid sodium filled exhaust valve in it. What that does is it helps with our heat transfer, having that liquid inside of it. The titanium intake valve is a 2.13 inch valve, and the exhaust valve is a 1.59 inch valve. Like I said a little earlier, this engine does have a 10-to-1 compression ratio. Guys, again, if you have any questions, please feel free to ask. We're with General Motors at the Performance Build Center, Bowling Green, Kentucky. We're the people that hand build these engines. This engine was just announced that it's going to be offered as a crate engine. So if you have any questions about the sales, availability, pricing, anything like that, please go over and see any of the guys in the red shirts. They'll be one of the dealerships that's selling this engine for us. So the question was, is it offered in long and short block? And it's not. It's only offered in a fully assembled engine. What's up? What Richard's got here is our valley cover. So like Brad said earlier, in a normal AFM engine, we'd have what's called a Loma. Because this is a non-AFM engine, we just go back to a traditional valley cover. One thing you will see on there, there's a little shiny piece sticking up out of the top there towards the front. That's our PCV that goes into the bottom of the supercharger. So that's your positive crankcase ventilation. Richard's holding our direct injection high pressure fuel pump right now. So like I said before, that tri-lobe in the camshaft, the mega lifter that we already installed, that's what's going to drive that high pressure fuel pump on the bottom of that. So that high pressure fuel pump's running right at 2,900 PSI. Brad, you want to talk a little bit about kind of the differences in that pump?
Yeah, so it's a slightly different pump than the LT1. The LT1 is a little bit lower pressure. It runs around 21 to 2200 PSI. It bolts up the same, so the gasket and the mounting flange are the same. It's just slightly taller, a little bit higher displacement pump.
So you'll notice we're talking a lot about direct injection. We keep emphasizing on direct injection. The reason behind that is because this engine runs two different fuel systems. It runs a direct injection and a port injection. So that direct injection where the pump's already stalled, we'll get our injectors in a little bit. You can see on our supercharger over here, our port fuel injectors are already in the supercharger themselves. So So Jason just torqued down our oil pressure sensor there in the front of the Loma. Next thing that's going in is our push rods. So this is still a small block, GM small block push rod engine. One of the things the builders would do when they get these push rods is they would look through them all with a light, making sure that it's very clean and clear, no FM or any kind of debris internal to the push rod. It's very crucial that we have good oil flow through those push rods. Next thing that's going on is our rockers. So in our normal build process, we do have a template or a fixture that goes on top of the head that helps us with aligning the rockers on top of the valve and on top of the push rod. Had someone mention earlier that you can see that everything's kind of tilted a little bit and not in a perfectly straight orientation. Those guides that we put on there really help us get those lined up and make sure everything's riding perfectly on top of the valve stem and also correctly on top of the push rod. So after we would get these rockers loose installed, we then go through a torque process on how we torque these, and it's a pretty special process. So we torque 8 at a time, and we torque the 8 that's as close to base circle as they can be. After we torque those 8, we then turn the engine over 360 degrees, which turns the camshaft 180 degrees, which puts the other 8 rockers as close to base circle as possible. The reason we do that is to get the spring tension off of the valve. We don't want to have to overcome that spring tension when we're torquing that down. It gives us a much better torque strategy and a lot better fit and finish on that once we get them run down. Those fixtures that I talked about earlier that are on there are color coded and numbered to make sure that the builder hits the green ones first and then the yellow ones second. So here comes our direct injection fuel injectors. You can see those are going to go right down into the head, and that's going to spray that fuel right down into the cylinder. Again, those are running at 2,900 PSI. That's how you oxidate. Atomize, that's the oxide. Next thing that we're going to put on is our valve covers. So if you look at the coil packs on the valve covers, these valve covers are unique to the LT5 because of how we put the coil packs on. If you look underneath there, there's a little stainless steel spacer that we use to raise that coil pack up off the rocker itself or off the valve cover. We had to do that because of the bigger supercharger and the port fuel injection. When we go to put this supercharger on here in a few minutes, you're going to see just how little room there is in there. So, like I said, we moved those out of the way.
Make sure that joint is not going to leak. So it's a ball and taper. They're a one-time use. And the reason we use helium is it's a smaller molecule than gasoline. So if there is a leak path there, we can force that leak path to happen at a lower pressure. So we tested that low pressure, 90 PSI. Safer for the operators, and it's a pretty quick, it's not the most exciting test to see run if you come in and build an engine, but it is a very critical and important process that we take every engine through. And then, I kind of talked about earlier, maybe a couple people missed it, when we scan in parts at every station. So you can kind of see here, there's a barcodes on all these components. They'll have to scan all those parts in to make sure they're the correct parts for the engine, and it'll track that serial number as that engine goes through its entire life. So that's just a good visual where you can see those barcodes.
So one thing I do want to point out while we don't have a supercharger on this engine That low pressure fuel feed pipe that we put on, the little pipe with the blue cap on it, you can see there's a T coming off of that where it connects to the high pressure pump. That T is what's going to supply our port fuel injection system. So that's coming in at sending unit pressure rather than off of the high pressure fuel pump. So Richard's going ahead and installing our water pump. This is a belt driven water pump. It is unique to the Corvette. All of the LT engines in the Corvette do share the same water pump. Jason's going to install our jumper harness here. So what this is just a little wire harness that connects our oil pressure sensor and also our water temperature sensor. It gives us one connection on the outskirts of the engine. We're going to cover that whole wire harness up and all those connections Jason just made. So we have to do that for the Corvette assembly on the dress line. When they go to dress this engine, they have to have a way to be able to make that connection. So we put that little wire harness on there just to make their lives a little easier. Richard's going to go ahead and install our balancer. So the balancer is new to the LT5. The LT5 does use a bigger belt for the blower, so we do have a wider rib balancer. You know, he made that look pretty easy installing that. That balancer is clearanced for ease today. In our shop, we press that on anywhere between 4,000 and 5,000 PSI. And I know that sounds like a lot to people. You know, the guys at home that are changing balancers out and things like that, they're like, why are you guys putting that on so hard? It's really hard to get off. And the reason behind that is we have to seat that balancer fully to torque our bolt. So to get a proper torque and be able to read that properly, we can't use the bolt to push the balancer on. So we push that on all the way first. Also, you got to remember, we're using brand new virgin parts, so all the tolerances are really tight. At home, for most of the guys, when they're changing out a balancer, it's already had one balancer on it, so it's not as hard to get the second one on the next time. Jason just installed an insulator pad there, that little piece of black foam. A lot of people think that's to help with heat, and the big reason that's there is to decrease noise. So with the high pressure fuel system and those injectors, we get a lot of ticking noises. A lot of people mistake that for lifter tick, and it's really just the high pressure fuel system. So we install these insulator pads to try to reduce some of that noise we got going through there. All right, so here's the fun part. Here's our new LT5 Supercharger. As you can see on the side, it does have the port fuel injection rails already installed. We don't like to do that at the demo events because it is hard to put those in. We do have to use lube to get those put into the Supercharger itself. The Supercharger is 55% larger over the LT4. With it being that much bigger, we are able to spin it slower, which also reduces heat. Its actual spec is a 2.65 liter blower. The throttle body is a 95 millimeter throttle body, which is the biggest throttle body GM has ever put on an engine. Something else that's pretty cool, sitting in the inside, is an electronically controlled bypass valve. That bypass valve is actually a throttle body off of the new Duramax engine.
So one thing you'll notice is there's a black Teflon-like coating on the rotors in there. That's a sacrificial layer that will wear into a perfect match. So if you were to take that supercharger lid off at 10,000 miles, you would probably see some bare exposed metal where that had worn away into a perfect fit. And then one other thing you can see here is it is a bigger blower. This blower at 14 PSI of boost turns about 15,000 RPMs on the rotor. The LT4 blower was turning 21,000 RPMs at 9 PSI of boost. So it turns a lot slower, makes more boost, and it's got larger cooling bricks, which Nate will talk about here in just a second.
Yeah, so just got a question on what's the horsepower and torque on this engine. So it is a 755 horsepower engine with 715 foot-pounds of torque. So our piece that Jason's holding here is our Supercharger cover. It does have our intercooler bricks built in. They are 30% larger than what the LT4 had to offer. Something else, now the intercooler bricks are in the cover rather than in the Supercharger themselves. The intercoolers do use its own separate antifreeze and its own separate cooling system. There's an electric pump that delivers and removes antifreeze from those intercoolers, then takes it to a heat exchanger out in the front of the car. Something that I do like to talk about, I just think is a cool fact about this engine. We can't sell this the ZR1 Corvette in Europe. The reason behind that is because the engine sticks out of the hood of the car. So Europe has laws, pedestrian laws, where there has to be so much gap between the hood and the engine. Because of that, we can't sell this engine in Europe. There's a really cool article out there that has a lot of information from our chief engineer, Jordan Lee, where he talks about kind of the aspects of how they designed this engine. And one of the key factors was being that they didn't want to sell it in Europe. Not being able to sell it in Europe allowed them to put a much bigger blower on the car.
So at this point, the last piece of testing equipment inside what we usually consider as the room. So in our facility, there's a four-wall, kind of a clean room type environment where the engines are built, and then after they go outside the room is where all the testing equipment is for after the engine's completed. But the last piece of test equipment that will go inside the room is our leak test. So we have some fixture plates that will bolt up, blocking off all the exhaust ports on the intake, all the coolant ports, and we'll fill the crankcase up with 2¼ PSI. And we'll fill the coolant system up with 20 PSI and look at a leak down rate. It takes about 1.5 minutes to run the test. We have very sensitive pressure transducers on that's reading that signal down to thousandths of a PSI. It'll calculate that based on how much the pressure drop is onto a leak rate, and as long as that's within our specifications, we'll allow the engine to go. We have a master engine that we run every single day. So it's a perfectly sealed up engine that we use to validate that leak test machine is functioning properly. There's no leaks in any hoses or anything that will give us some false readings that the engine was leaking. So it's kind of the last validation test before the engine was now kind of completed and would go out to future testing, which I'll talk about here in a little bit.
A couple other things we got going on the engine right now. Jason's holding up our Y pipe. So that Y pipe is going to be the final connection from that low pressure fuel feed into our port fuel injection rails. So like I said before, that port fuel injection is going to be running at fuel sending unit pressure. The port fuel injection is only going to be operated under high engine loads. Under high engine loads, it can supply up to 20% of fuel demand on the engine. Those things are not only necessary for performance, but also for protecting the engine. By putting more fuel into the engine, we're able to keep it cooler and protect our exhaust components. They're installing the coil wire harness now. So they just put that on there. They're making 8 connections, connecting all the coil packs. Again, something that we do for Corvette assembly to make their lives a little easier. They only have to make 2 connections now on the dress line. So we're getting spark plugs in. Each of the LT engines have a unique spark plug. They'll range just a little bit in different heats and temperatures. Something else I do want to mention right now, with how our program is and one builder building the entire engine, we install a nameplate on all our engines from which builder installed it. On the LT5, we put a nameplate on the back left side of the Supercharger. So if you see any ZR1s out today, or if you own one, pop your hood up and look down there and see which engine builder built it. All the LT4 engines that we build for the Z06 cars, we also install a name tag on. That nameplate goes on the front of the engine, on the crossover pipe for the intercooler. We said it's going to say built with pride or handcrafted with pride by, like a Jason Neal or Richard LaRue. What that does for us is, it gives everybody a sense of pride in what they're doing. It really helps our quality system. With a builder being able to put their own name on it and assign it and say, hey, I'm the guy that built this, it really increases our quality because they want it to do well. They want the customers to be happy. Next thing that's going on that's very crucial to the engine is our knock sensors. So our knock sensors are what's checking for any kind of spark knock or detonation in the engine. Without those, it would be detrimental to the engine. Would also hamper performance, but could also, explode the engine. Those are just little microphones that's looking for that spark knock or detonation, so that we can adjust timing or any kind of fuel delivery. Okay, so I just want to re-emphasize here. We're from Bowling Green Assembly, the Corvette assembly plant. We're the Performance Build Center, so we are the people that handcraft these engines. This engine was just recently announced that it's going to be offered as a crate engine. If you're interested in the crate engine and any of the sales or specs or availability, please go see any of the guys in the red shirts over there. They're one of the dealers that's going to be helping sell this engine. As our builders are kind of finishing up here, I want to thank everybody for coming out. We still have a lot of good information, so please don't leave if you want to hear some more specs. But I'm going to let Brad, I'm going to hand it over to Brad, let him go through some of our testing equipment we do after the engine's completely assembled.
Yeah, so we cold test every engine. So we don't dyno them, we don't fire them up. Every engine goes through our cold test process. We call it cold test because we're not actually going to fire it up. What we're going to do is we're going to move this engine after it goes outside of the room onto another cart and load it into our cold test stand. The cold test stand has a bunch of connections that they hook up to the engine, all on the front cover connections. One of the cool things I like to talk about is the spark probes. So when the builders are installing the spark plugs, we don't have to check gap. We don't do any inspection on the spark plugs because the probes that go on those can actually calculate the gap based on the current feedback that it sees from those probes. And also has a ring that charges around the ceramic, that if there was a crack in the ceramic, it'll arc between them and we can catch a defective spark plug. Cold test is a very in-depth machine. There's a couple thousand test points. And I'll kind of give you a high level detail of some of the things that I think is neat about the test. If you want any details or any specifics on what we really do to test the engines, come by and see me afterwards and I can really walk you through it. What we'll do is, again, like torque to turn, we'll check the breakaway torque, make sure the engine's not too tight to roll over. We'll check oil pressure. So we install our own oil pressure transducer right off the main engine oil rifle. My sensor that I hook up can collect data a lot faster than the on-engine oil pressure sensor. So we see a very spiky oil pressure signal that can see pressure fluctuations from each little rotor of the oil pump. So looking to kind of check a defect in one rotor where if the oil pressure sensor on the engine can't see it, it's more of an averaged out signal. We'll activate that AFM if it was an LT1 and LT4 engine. We have quick connects that we put on the exhaust with a pressure transducer. When those 4 cylinders drop out, we see a change in exhaust pressure trace. So we make sure that that system is working properly and then turning back off. We'll actuate the variable valve timing. So as we kind of talked about earlier, it's sitting at 7 degrees advanced. We'll take it from its fully advanced park position to the retarded position. We'll measure how long it takes to get there and make sure it gets to the correct position and returns to the correct position. We'll activate the variable displacement oil pump, so we'll take it from its high pressure oil setting down to its low pressure setting and then turn it back off. One of the cool tests that I like, it's called the torque test. So it's a big electric drive motor that's actually turning the engine over. We'll grab onto the flywheel or flex plate with a couple grippers, and we use that electric drive motor as a torque transducer as well. So because we're not firing the engine, as you come on that compression stroke, if you think about it, that air is a spring, you're going to compress that spring. Because you're not firing it, that spring is going to push back, so you actually get a positive to negative torque on the drive motor. Every cylinder should be about the same, so it should be a really nice sinusoidal wave. If there was a cylinder that didn't kind of have a squinch in its wave, I can tell you that there's low compression on a cylinder without ever hooking up a compression tester. So it's a really neat test. Same thing with the intake. So we'll put a pressure transducer right on the intake. With the cam and crank timing that the sensor, the engine can read from the test booth, I can overlay each cylinder's intake vacuum pull. So I can check valve opening and closing events to make sure that we don't have a soft lifter, then every valve is opening and closing properly. So there's a lot more that goes into it, but we'll ramp the engine down. We actually fill these engines by weight instead of by volume. Because it is a dry sump system, we don't exactly know how much oil is retained in the engine afterwards. So when the engine comes out of the room, it has a dry weight, and they will add 24.6 pounds of oil to it with the spark plugs and the heat shield. One last thing that I'll kind of talk about, do you have a question?
You have 2 knock sensors.
2 knock sensors? There is 2 knock sensors, one on each side of the engine. Yeah. So the one last thing I'll talk about is our balance stand. So only manual transmission engines go through balance, and actually only Corvette engines go through balance. The reason we balance the manual transmission cars is due to the geometry of the Corvette. The shifter is mounted to the torque tube, and we had some customer feedback that said, hey, I don't really like that my stick shift shakes in my $100-and-some thousand car. So we'll put these on a balance stand, we fire them up. It's not a dyno, it's really just an engine running at 1500 RPM on a floating table. That table is calibrated to tell us where to add weight So there's holes in the balancer and on the flywheel in the engine. We'll put weights in and rerun it until it gets within ½ an ounce inch front and rear of externally balanced. That has nothing to do with the rotating assembly. Right? The rotating assembly is still balanced. It's more of an aesthetic thing for the Corvette. It's the only engine in General Motors that is externally balanced for that reason. So that's the only thing that we do to fire them up. We don't actually dyno them. That cold test machine is a really good way to test an engine and validate it without ever having to run it. That kind of completes it. If you have any questions, stop by and talk to me. Give the builders a hand. They've been doing this a lot this week. And we'll be around if you have any questions. Thank you.
Thanks for joining us, guys.
You hear it run? Not this one. Do you know what the coolant capacity of the door is? I know that the LT4 had problems overheating here on the track, and but since you said it's a much bigger one, turning a lot slower, I'd imagine it does better.
He's our quality engineer.
Appreciate it.
What kind of